When studying organic chemistry, we want a basic idea of what happened in general chemistry. So in general chemistry, we put together individual atoms. So for organic, what we're going to do is now look at a limited amount of elements, and in particular carbon. So if we're going to look at the structure of a carbon atom, should remember that we've got a nucleus and then the outside the nucleus section. Within our nucleus, we're composed of our protons and neutrons, and then outside that nucleus, we have the electrons. As in theory you remember from Gen Chem, our protons will define the element, and then our neutrons together with the protons end up defining the the mass. I tend to separate those into two separate components because if you change the number of protons, the element absolutely changes. If you change the number of neutrons, your mass will change for that particular element. So it's still dependent on the protons, but it makes a little bit more sense to separate it this way. And as far as the protons and neutrons go, it's not going to be all that big of a deal, except when you're looking at mass spectrometry, so MS. Okay, when you look at that, you will need to be aware of what the different masses are of different isotopes and be aware of those isotope effects. What we're going to be primarily concerned about with organic is the electrons. And those electrons will exist in individual orbitals that have been defined by physics and mathematics and all sorts of other fun stuff, which we won't have to worry about. It's the balance of the electrons and the protons that determines our charge, as we remember from Gen Chem. But much more importantly for organic chemistry, it's really going to determine our reactivity. So it's looking at how those electrons on the exterior of the atom interact with electrons on the exterior of another atom. So if we were going to look at two atoms coming near each other, it's the electrons that are going to first interact with each other. And it's really those electrons seeing the nucleus of another atom that's generating that new interaction. So what we're really concerned about is the balance of where our electrons exist and how they can move around between atom and atom. So when we look at our atomic orbitals, so if we just look at an individual atom, you should remember that our orbitals will break up into different energy levels. We can only put 2 electrons in an individual orbital before we have to move to a new orbital. We start with the 1s electron, shown at the bottom, which is spherical in shape. Once we dump 2 electrons in, we move up in energy to our 2s, or our second energy level. Within that second energy level, we have the s orbitals and our p orbitals. Notice that there is a change in shape, and the primary difference that you'll hear referenced is there's an increase in the number of nodes, which means there is 0 electron density in that position. So if we looked at the electron density map for the s orbital, you'll notice there aren't any nodes. There's no place where you have 0 electron density. But if you shift to the p orbital, right in the middle, we have no electron density, so 0 electron density. So we have a node. That results in a shape that gives us the dumbbell shape for our p orbitals. Within these, our s and p, or 2s and 2b, are very close in energy. So that energy difference is very, very small. This is what ends up allowing us to do hybridization later on when we look at building molecules. When we look at size, the s versus the p again, our p orbital is larger, which means it's slightly further from the nucleus. So the more our electrons are in p orbitals, the less tightly they're held to the nucleus, which would apply back to electronegativity, which we'll talk about here on our next slide. So what we're looking at is where these electrons can shift around. So when we looked at the atoms back in Gen Chem, you talked about 2 concepts, the electron affinity and the ionization energy. The electron affinity was the energy released when we absorbed an electron from the vacuum. Remember, our electrons are highly, highly unstable, so as soon as we associate them with an atom, we lose some of that energy, that excess energy, so they become more stable. We could also look at the ionization energy, and this is the energy required to remove an electron from an atom into the vacuum. And it turns out not all elements are created equal in these 2 respects. Pauling came along and was one of the first people to take these atomic effects and translate them into a molecular understanding. meaning that when we bring two atoms together, he was able to come up with a number system to say which one of those atoms would prefer to take the electrons in that interaction. Okay? And he defined that as electronegativity. So you may or may not remember a table along, or a periodic table along these images, where we're showing an increase in electronegativity in the upper right, so fluorine being the most electronegative, and then we see it kind of decrease down and to the left across the periodic table. Having an understanding of electronegativity is critical to understanding resonance, reactivity, bonding, intermolecular forces. Everything in organic chemistry really kind of revolves around this process of understanding electronegativity. Okay? And ultimately, as we saw from the previous slide, electronegativity is also dependent on a little bit on size. So we need to be aware and processing these two concepts of electronegativity and of size. So electronegativity is defined as the attraction for bonding electrons. It's very, very particular. So we're always looking at a bond and where those electrons spend most of their time. Okay? So when we take two atoms and we bring them near each other, we end up with two possible results. We can either end up with a situation where the electrons see the other nucleus, in which case our electrons are being shared between the atoms and we now have a bond. Or we run into the other situation where our electrons stick with their own nucleus, in which case there's no bond. Okay? In that no bond category, we can run into a variety of different types of interactions. Okay? And some of that is going to be dependent on our electronegativities. So we end up with these two subcategories. So in intramolecular, intramolecular interaction, we're looking at bonds, and intermolecular, we're looking at forces. So intra, within, inter, external. And we've gone through and subcategorized these interactions according to particular groups. So we get ionic and polar covalent and covalent as our bond classifications. Okay, so it's really important that if you're asked to identify a bond, you're existing only with these three categories, at least as far as organics concerned. If you're asked about the type of force, well, that means you're going to exist over on this other category with those four interactions. And you need to be able to keep these both separate and realize that they are connected to each other. So how do you go through and identify these? Well, as you may remember, in some cases, an ionic interaction or an ionic bond is between a metal and a nonmetal. There are more strict definitions. Those strict definitions go back to electronegativity. So if the difference between the electronegativities, shown as I believe it's a chi, is greater than 1.7, then it's defined as an ionic bond. But then you'd have to know all the electronegativities. So we want to do a step away from having to memorize those and come up with simpler rules. Okay, and that's what these simpler rules are showing here. These are not perfect, so we shouldn't actually call them rules. They're recommendations. They get you pretty darn close to determining your answers. Once you know the type of bond that you have, for instance, an ionic bond is between a metal and a nonmetal. Well, one of the characteristics you might see would be a plus and a minus. Well, if I now know what the bond is, what kind of forces would I expect out of that? Well, it turns out the forces I would expect would be between ions, electrostatic. Okay, so that's kind of a neat pairing. What happens if we look at our covalent bonds? Well, that's between a nonmetal and a nonmetal. But so are polar covalent. So that's when we bring in same electronegativity and the extra category of a carbon bound to a hydrogen. Well, what kind of interaction would I expect between two molecules that just have covalent bonding? Well, that's where we get our London dispersion forces. Okay, interactions between two covalently bound molecules. So the idea behind this slide is setting this up and recognizing that we can start to do translations or parallels between each of these interactions, okay, between both the bond and the forces. So they are directly related. So if you can identify the bond, you can identify the force, which is really, really powerful. if we kind of organize this into kind of a color diagram, we can look at that same kind of slide as we did before, except now what we've done is turned it into a circle. And what we're looking at is increasing the polarity, and I should actually change that arrow a little bit. We increase the polarity as we go straight up. And that occurs on both sides of this diagram. We get more polar molecules because we have more charge as we become more ionic. If we look at the strength of the interaction, okay, well, in London dispersion, it's a very weak interaction. As we go up to dipole-dipole, it gets stronger. Hydrogen bonding, stronger still. Ionic, stronger still. Why? Because of that polarity. We have a positive and negative. We want to stabilize those charges. If we increase that interaction even further, we move from an ionic force to an ionic bond. Now, as a bond, it's much, much stronger. That bond can then get even stronger still, and we reduce that charge differential between the two atoms. So we get an even stronger interaction. If we continue to make that interaction stronger, we end up back at our covalent bond. Okay? So our strength of interaction actually does fall around the full circle. The polarity of our bonds goes just vertical straight up. Okay? And why is this important? Well, we can look at melting points. We can look at boiling points. We can look at solubilities and vapor pressures. All of those physical properties are dependent on the forces. So what we can do is just look at the interactions, or look at the structure, determine our bonds. Once we know the bond, then translate that across to our intermolecular force. We can then compare that to, say, another molecule, say something that's a covalent bond, over to London dispersion force. Well, the London dispersion force is much weaker than, say, a hydrogen bonding force, so I would expect its melting point to be much lower than the other compounds. So we can do a lot of comparative things by understanding these forces. If we directly evaluate the bonds, we can actually determine something about the reactivity. We can look at acid-base reactions, substitution, elimination. All of our reactions ultimately fall out of the types of polarities generated by our bonds. If we have a very strong bond, for instance, if we have a covalent bond, we see very limited reactivity, which we'll talk about when we look at our functional groups in a later discussion. Okay? So this is just kind of a way to bring it all together and kind of summarize what we're looking at. When we look at our bonds, it's important to look at Lewis structures. So what we've got here are two simplifications for our Lewis structures. On the left, in the red box, we're looking at what I would define as my Lewis structure building rules. We usually kind of step away from those strict rules in organic chemistry and move into kind of the simplifications. Be aware of all of those simplifications in the blue box. The ones that are going to become very, very relevant for you very, very quickly. We're looking at hydrogen being implied to carbons and lone pairs being implied to nitrogen, oxygen, and our halogens. So make sure you're aware of those two issues, because those will drastically change how we can go through and do a reaction. We then also go through and use Vesper and Lewis structures to draw representations of each structure. So if I wanted to draw ethane with the formula C2H, I can count 6, we could go through and draw out our ethane by showing the bonds, hence the electrons, between all of those atoms. And those electrons, or our bonds, are represented by those lines. Okay? We could also go through and do something like ethanol. So, very simple adjustment to our overall structure. We could draw it out where now we introduce an oxygen. Okay, and we put that down, and we now have ethanol within our structure. If we just look at these two drawings, we would probably just assume they're roughly the same. We don't have to worry too much about the chemistry. But remember, with organic chemistry, focus on the electrons. When you draw these out, this is not how you should be seeing them. Okay? What you should visualize is where the electron density is located. Well, the bonds found between carbon and hydrogen are all nonpolar covalent bonds, which means no charges. If we go through and take a look at the bond in our alcohol, both of those bonds are polar covalent bonds, which generates a much larger charge. So our electrons are now imbalanced in that structure. That imbalance brings in potential chemistry. So instead of looking at these as Lewis structures, there's no way we'll ever draw this, but look at them as far as the electron density. So when we look at our ethane, really the electron density, shown in red, is embedded in the middle of the structure. Well, that's pretty useless as far as chemistry goes because the electrons are now stuck inside. If we move over to ethanol and we look at that same red section, we have the electron density on the outside of the structure. That means those electrons can potentially react. So never, never, never forget the electrons. Think about the balance of where those electrons exist within the structure and always focus on that. Okay? So, a little bit of quick practice. So there's some practice problems here. I'm going to go ahead and tell you that it is time to pause. Go ahead and work those problems, and I'll be back in just a second. Hopefully you've had time to figure out all your answers. Question number 1, I split it into 2 categories, blue for the total number of electrons for that atom, and then red for our valence electrons for an individual atom. Hopefully that's self-explanatory. I will mention that you have to watch out for those charges, and I was intentionally tricky with deuterium. Deuterium is just hydrogen. Provide the mass and percent abundance, if possible, for the following atoms. So carbon-14, the first two, carbon-14 and bromine-81, both of those are common or isotopes of carbon, or isotopes of their respective elements. Carbon-14 is 1 part per trillion, so within a trillion molecules, one of them is carbon-14. Its mass is 14. That's why that number is there. For bromine-81, we've specified that 81 in a slightly different location, which you're also responsible for knowing, and its mass is roughly 50%. It's a little bit, or percent abundance is roughly 50%. It's actually a little bit under that. For the oxygen, I didn't specify an isotope, so we can't really specify an abundance. Its mass is 15.999. For all intents and purposes, your calculations, 16 is a pretty awesome number. Hydrogen plus 1, so hydrogen in its charged state. We've lost an electron, but that doesn't affect the mass. It's still 1.008 as far as the mass. We had to include all those decimals because we didn't specify sort of really which atom it was. If we did specify that that is specifically hydrogen and not deuterium, or tritium for that matter, our percent abundance is 99.99%, so pretty freaking high percentage. In question 3, hopefully those charges all make sense. The bonds should all make sense. The one that I didn't have enough space to really put in there is part C. Identify the forces. So you got to be careful with this. I just said forces, so that's pretty much all forces. Every single one of those has London dispersion forces as a possibility because they have electrons. So what you need to do is identify the strongest force possible within that molecule by identifying the bond, and every force that is weaker than that is a potential, except for hydrogen bonding. So for that first one with a covalent bond, only London dispersion. For the magnesium-carbon, it's an ionic bond, so we get an electrostatic force. We don't have the rules to satisfy hydrogen bonding, so that's not included, but by definition, we will have a dipole. So we have dipole-dipole, and we'll still have London dispersion because we have electrons. So hopefully that makes sense. Where our intermolecular forces become more important is when we move into question 4, and we want to go through and rank them according to our solubilities. Well, in our solubilities, we're comparing to water, which is hydrogen bonding. So the more polar the molecule, the more soluble it's going to be. The magnesium-carbon, having the ionic intermolecular force, is going to be the most soluble in water, followed by the OH, which is almost identical. The carbon-oxygen being more polar than the carbon-hydrogen, okay, and so on. Within the Lewis structures, I decided to run with the abbreviated structures. Hopefully those all make sense. The blue one is a little bit tricky because that line formula doesn't specify whether it's cis or trans, so we could be looking for both answers. I drew the trans. The last one is extra tricky because we're looking at just a formula. Formulas suck because too many different things can come out of them. So I drew two structures that could have that exact same formula. Hopefully you got all those correct. If you got any questions, you can always feel free to contact me.